Okay, so let's see. We left off looking at, under this organizational chart of bonding for molecules, we talked about, like, from high school. A lot of it starts with the Bohr-Rutherford or Lewis theory, count the electrons and make dot diagrams and that type of thing. It's a non-quantum mechanical model. And then we talked about the quantum model, what it means to do the real quantum mechanical treatment. And the real quantum mechanical treatment is related to the box or the cage that exists for, in all of chemistry and bonding, our focus is on the tiny little particle we're interested in is the electrons that are in the system. So all of the positively charged nuclei are essentially treated as part of the box, the trap, the cage, the containment holding the electrons. And what you will get, just like in a single atom by itself, you got orbitals. Well, the molecule creates this big cage or box, and you get molecular orbitals resulting from that. So it takes powerful computers to do that, to do a decent job of it, to give you a good estimate of the energy levels, the molecular orbitals, and the resulting shapes. So what has been developed and used for a very long period of time, and nowadays is used first year and beyond all the time, Valence Bond Theory. It's still something that us as humans, we use this conventional model. Valence Bond Theory deals a lot with the concept of hybridization orbitals. Okay, and we all know that hybrid orbitals don't actually exist, but even those hybrid orbitals were essentially mathematically generated by mixing together sp d-type orbitals. I do a little slight energy minimization to talk about the best way of bonding and pointing it right at the very thing it's bonding to. So we moved on to showing the well-defined and still used method, and we went to single stick or single bond molecules. So that's the classic teeter-totter type thing and that sort of thing. Well, now today we're going to go to organic molecules. So this is sort of like a special case of the well-defined, still very much used in organic chemistry all the time. Slight changes to a few of the things we did for the single bond, single stick molecules and bonding. So for organic, we're going to start with, and I just want to go over what is essentially, so organic molecules. So a perfect example of that is one of the simplest ones. If you look it up, the molecule is ethene. You know, there might be some common names from before. I believe it's acetylene or something like that. But you have two carbons, and you have, for the first time, you're looking at it now, a double bond. So this is sort of a think bubble to say, look, what's going on here? Well, the double bond, one is going to be called, in organic, a sigma bond. And then the other one is going to be called a pi bond. Now, sigma bonds, whenever you get into organic molecules, the one thing is always true. How about this? The pi bond is the one that essentially goes on to make or complete the double bond. Okay? And then even if you had a molecule like this, geometry, Mike. Okay, this is a triple bond one. So one of these sticks is still the sigma bond, and then these other two would be called pi and pi. So there's two pi bonds. So pi bonds, okay, the second or the third stick like this of a multi-bond, the idea is they are p orbitals on each of the carbons. And what they'll do is they'll say they overlap this way. So a pi bond is made by each atom that has them sharing one electron from each of their pi bonds, overlap the p orbitals to get a pi bond itself. Okay, so that's the pi bond. And in this case, you're going to have two of those sticks, which are pi, are done this way. All other, even this one is called a sigma carbon-hydrogen bond. This one would be a sigma bond between each of the carbons. So all single It's almost like you call it the single bond. The first bond made is the single bond, which is a sigma. They're all made from sp, whatever number, depending, you'll see, but they're sp hybrids. So just like we've seen in the single stick model, all hybrid orbitals look similar to something like this, and they point directly at what you want to bond. So the sigma bond structure of organic molecules, the very first stick out of a multi-bond, double bond or triple bond, the first one is a sigma bond, and they're made by hybrid orbitals. The remainder of the pi bonds, if you have them, are made by the overlap of p orbitals to make the pi bond. So that's sort of the new wrinkle. And just to flesh this out before we start, you could even have something like this. You could have formaldehyde. You could have cyanide. You could even have nitrogen. You could have oxygen. You could have some kind of... Well, we'll get into the the nitrogen and oxygen type of molecules. We'll do those in a separate class later, just to handle a few of the slightly different parts about them. So we're looking at, anyways, this one. You would label it. The first one of the two you're counting, that's a sigma bond. And that's made from the sp type of hybrids. Sp with whatever number you need will do that, hybrids. The other one is automatically a pi bond, which is made from the p orbitals overlapping. So by default then, what this is going to tell you is this oxygen is going to have an electron in a p orbital. This carbon is going to have an electron in its p orbital. They overlap to make the pi bond. And we'll draw you a picture of that as we get through it. This one, carbon-nitrogen, triple bond. Well, the very first one has to be a sigma bond. Yet again, each one of these is going to use its sp, whatever number we get to, hybrid orbitals that look like this. They face each. So I could even start right now saying what that means is the carbon is going to have one of its hybrid orbitals. The nitrogen is going to have one. They overlap. That is the sigma bond. So now the remaining two sticks have to be made. These are the pi bonds, two of them, because it's a triple bond. And each of these has to have p orbitals. So there's got to be one p orbital kind of looking like that. This one has one here, and they're going to show in pictures they overlap somehow like that. So that's one of the pi bonds. Then the other one, if I could show the geometry of another p orbital coming straight out and behind the page, so I'll kind of draw an axis to say it's like your z-axis coming out, right? So I'll exaggerate it. It goes way back. This one goes way, like this. Pi and pi. These are the types of pictures you're going to see in a lot of the organic chemistry textbooks, etc. And then nitrogen, same thing. First one is a sigma type of bond, again made by the hybrid orbitals on each of these that overlap, right? And those hybrid orbitals look like the standard thing like that, a bigger part, smaller part. And then these two are pi's. This has one sigma, this has one pi. So in organic chemistry, especially when you get into organic mechanisms, etc., the concept that I just showed here, talking about the sigma bonds versus the pi bonds, this is a mainstay of the lingo and how we have to start thinking about it. Now, I would point out, somebody could say, well, how do you know, for instance, how do you know that its shape is automatically like this? Because carbon, nitrogen, and oxygen in the organic molecules, it's so typical and repetitive, you quickly essentially, you do it so much you just know there's a limited number of geometries. So you quickly get used to how to draw them out. I'll give you an example. If somebody wants an example of an aldehyde, you learn the aldehyde functional group is something like that, right? So the aldehyde functional group, you'll start almost remembering what this is like. And then the other thing in organic is when you draw this zigzag shape, I could blow up one of these, for instance. You know that there's a carbon, and we already know that carbon is tetrahedral. Well, the way I drew it here, these two hydrogens, one of them would be behind, one is coming out. But if I blew that up, you'd say that carbon is going to look like this. So the two sticks drawn in the plane of the page are the two of the tetrahedral shape we already learned about, the single stick model for that one carbon I've blown up. The other two sticks, one is coming, this one is going behind the page, this one's coming out at you, right? So you get used to this. When you want to look at this one, you automatically start remembering that that carbon is going to be sp2 hybridized, and this one by default is also going to be sp2. So what that means is for each of them, if I'm only going to be sp2 hybridized, which we've already introduced ourselves to, you're going to see how you're circling an s and two p's. So you have 1, 2, 3, and then the p orbital remains. So what they're basically going to tell you is, and they're going to break a little bit of a rule here, is for instance, if this was the carbon, and this could be the oxygen. So both the carbon, the oxygen would look like that. This has one stick going back to another carbon. So there's 2 electrons there. So this carbon could use one of its sp2 hybrid orbitals that look like this, right here, and it could bond to this carbon. So I could write in that carbon its unbonded electron. The other one, it's using one of its unpaired electrons to bond to a hydrogen, so I could bring that hydrogen right here. What's left? 2 sticks. This carbon has to have 2 unpaired electrons. We've already discussed one of them in a sigma bond has to be an sp2 hybridized orbital, which this carbon we have right here. This oxygen has the same thing going on, so this one is going to hook up right here. This would be your sigma bond. The new wrinkle in this program is, or conventional model is, we break the Hund's rule. Remember how it said when you have different energies, you're not supposed to be able to put an unpaired electron here. This one should have been in here while filling up. Well, this is a model we need to have the p orbitals with an electron in them. Okay, so we just basically say in this model that's just the way it is, because it's not like we're doing real quantum mechanical numerical analysis treatment. This is a model, so we say these 2 overlap, and that keeps the integrity of what the pi bond, right? Because when these 2 overlap, they both have these p orbitals looking like that, and they overlap. So that's a taste of what it would be like. And then how do we know this? Again, what I was pointing out is you could even go to things like if you have a triple bond present, and then, this could be a hydrogen like that with another one and another one, and this could go on to some other carbon and so on. You're going to pretty much get used to the fact that the limited number of geometries and bond structures for carbon, nitrogen, and oxygen, a little bit of memory, a little bit of practice will get you to feel comfortable with it. So now let's go on to how we're going to start this. So to do this more appropriately, I guess we'll start with ethene. So here is ethene. You might see a picture of it. Now somebody's going to say, show the bonding analysis, if you will. So I'm going to call this carbon 1, and I'll call that carbon 2. And that's fine. We've already started this off by telling ourselves, we know, and this is part of the model, you know that one of these sticks has to be a sigma style bond, because we've been told so. And we also know that these are done where each one of them is going to use a hybrid orbital, right? So carbon 1 would use 1. This one, carbon 2, would use its hybrid orbital to do the overlap and make the sigma bond. Sigma stands for cylindrical symmetry, which if you put your eyeball here and you look down the bonding axis, when you're looking at it, it looks like what they call cylindrical symmetry. So when you're looking this way, cylindrical tight electron density, the symmetry of it. So how are we going to do this? We know we need hybrid orbitals, and then the other thing we've also been told is that the other remaining sticks are also going to be hybrid orbitals. So how are we going to make this carbon have 1, 2, 3? How are we going to have it have 1, 2, 3 hybrid orbitals? Well, I think we already know they're going to be called sp2s. So I could say, okay, here is, and I'm going to draw carbon 1 here. So here would be carbon 1 by itself. And we know it looks like this. This is the 2s, and this is the 2p. So if we're going to hybridize this, we're going to circle this, and we're going to get 1, 2, 3. So this is carbon 1 hybridized, reconfigured. It has 3 sp2s. They all look like this. And the 2p would be left here. Now, in our previous model, we would only put these electrons in the hybridized orbitals. The leftover either d orbital or a p orbital, we would just leave it alone. That's the new wrinkle here. We know that this other one has to be a pi bond, and we know that we're going to need p orbitals. So that's the new little front end of knowing a little bit where we have to go with this. So we're going to break that off-bow or filling in principle. We're going to go 1, 2, 3, and we know we need to have an electron here. So even though it's higher energy, we're going to break previous rules of filling in, electron configuration, all that jazz, because we have to. So this is carbon 1. Now, by default, one of the other rules is whatever hybridization. So now we know that this carbon is sp2. This one is also sp2 hybridized. And we're thinking, bubbling back to when you have a carbon-oxygen double bond, they're both sp2. So what you're going to quickly learn, or if you have a triple bond, this one is going to end up being sp, this one's going to be sp. So you're going to quickly learn that any kind of double bond between carbons, carbon-oxygen, carbon-nitrogen, whatever, if it's a double bond, each of them will be sp2, just like each of these is sp2. And if it's a triple bond, each one will be sp hybridized. So it's a little bit of a you know before you start where you're going. So we got this. So that means carbon 2, I'm going to redraw carbon 2 hybridized up here. And it's going to look the exact same way. Right? So now you're going to say, okay, carbon 1. And I'll call this hydrogen A, I'll call this hydrogen B, I'll call this hydrogen C, and hydrogen D. Carbon 1. We know that each one of these sticks is built up of, carbon 1 has to have 1, 2, 3, 4 of its own electrons. 1, 2, 3, 4. Unpaired, ready to make bonds. Okay. Carbon 1 needs to hook up with hydrogen B. And hydrogen B comes to this little bonding party, and I'll make little triangles for them. It's 1 electron. So I could walk over here and say, look, like a docking site, here is one of those hydrogens. I could call that hydrogen B, doesn't really matter. Hydrogen A. So there's the 2 hydrogens. That's on carbon 1. And then carbon 2. Carbon 2 is going to have, and I'll draw little squares for its 4 electrons. So do you see how I'm starting to even do housekeeping or accounting on a structure like this? I know that carbons come to the party with 4 of its own electrons. That's why the charge on this one right now, the ownership, looks like it still has 4. So that's why it's neutral. Hydrogen brings 1, the other one, carbon, brings 4. So now, how am I going to make the first stick? Do you see how this carbon needs 1 of its hybrid sigma bond electrons? This carbon 2 needs 1 of its as well. So I'm going to go over here and say, well, this last hybrid on carbon 1 has to hook up with 1 of the hybrids on carbon 2. So I'm just going to connect these two to say these would overlap. Okay? And this would make your sigma stick or bond in this diagram. Carbon 2, we know that it's going to have hydrogen C, for instance. Bring its hydrogen D. Brings its. And then what's left over is the overlap of the remaining. Each of the carbons can have this overlap. Now, what's interesting is when you're going to do this analysis and start drawing a picture, we always focus, you sort of focus on the SP, the SP2, or the SP3 shape. In other words, leave the p orbital bonding overlap for dead last. Pretend it's not even there for drawing purposes at the moment. Come back to it later. Focus on the hybrids. I don't care if it was SP, SP2, or even SP3. If it's SP3, are you going to have any remaining p's left over? No, you're not. So I guess I should say for this multi-bonding thing, we can leave SP3 out for the moment because you don't have to worry about any leftover p orbitals to make pi bonds. So when you have those, so sp2, here's your carbon, and we already know how many regions of electron density that's in this giant square. This carbon, I got to focus on carbon 1. So carbon 1 has 1, 2, 3 regions of electron density. So therefore, you're going to have this trigonal planar geometry, just like we used in the previous model. But now, you're automatically going to draw in the hybrid orbitals. I'll leave off the tail on the other side, just because it starts making it look a little funny. This one's going to have another one pointing that way, and another one pointing this way. So an sp2 hybridized carbon has on it 3 hybrid orbitals looking like this at 120 degrees. That's the geometry of that carbon. Carbon 2 is going to do the same thing. 120 degree bond angle. It's going to have its own, and they're going to overlap. It's going to have its own sp2 hybridized orbitals look like that. And now you can say, okay, I can draw on hydrogen A and B on carbon 1. So here's hydrogen, I don't know, B has an s orbital for that overlap. This is the model and the convention of how they do it and show it. Okay? So orbital overlap and hybrid orbitals in the model we use do exist, but it's a model. Just like an ideal gas does not actually exist for real, but it's a great useful model. So did everybody agree? Looking at only carbon 1 and carbon 2 and each of its hybridized orbitals, each of them have 1, 2, 3 regions of electron density in here. Therefore, you get the shape of trigonal planar. Each of them is trigonal planar. This is the sigma bond between the carbons, sigma bonds between carbon hydrogens. So now we draw on the p orbitals. And we all know that p orbitals are related to the x, y, and z axes. We only have one remaining one. So for the sake of drawing on paper, I would probably say, and the other thing I should point out, I'm going to redraw this in a minute to finish addressing completely stereochemistry. All I did here was draw pictures of the overlaps. So what I'm going to do is I'm going to say, let's hold off on the specific geometry for a moment. We'll come back to it and redraw it more appropriately. Let's just say we know there's going to be a remaining p orbital on each. And we needed an electron to be in it, otherwise that p orbital would not exist. We don't perfectly try and draw them so, bulbous, because it just looks ugly. So what a lot of them do is they'll show you how these two lobes are overlapping. This is the pi bond. So they will draw shadings like this. Okay? So in other words, too, we'll come to the geometry in a minute, that would be an orbital overlap picture of ethene. So what we'll do now, I'm going to leave this up top, and we're going to redo that part a little bit with better geometry. So now what we're going to do is we'll keep in mind x, y, and z. I'm going to pretend we're going to use the p orbitals because y and x is in the plane of this page. Z is supposed to be sort of coming out. So I'm going to say, let's pretend we're going to use py orbitals. That being said, carbon 1, we know it's going to be trigonal planar. Carbon 2 is going to be trigonal planar. One of those lobes of the sp2s has to go like this. So do you see how it's in the plane of the page? It's almost like in the x direction they're overlapping. But what I want to do, because this is trigonal planar, I want to show the other two sticks being almost like it's facing you like this. So I'm going to purposely make the hash mark. So what that means is, if I had the previous drawing, if I was to have those two hydrogen sticks, if it was literally in the plane of the page, so let's pretend, I'm trying to make a 120 degree angle here. So you could arguably say, let's pretend this is carbon, and these are two hydrogens on the end of the pens. 120 degrees. See how it's in the plane of the page? But the problem is, to draw the p orbital is going to be 90 degrees to this, coming directly out. So for the ease of drawing this picture for the p orbitals, see how the dashed line means that that stick is going behind the page. This one's coming right out at you. So it would be like taking these two like this, and I'm going to rotate it like this. So remember how this blue one used to be flat in the page and the red one was there in the page. Now I'm rotating it. So the red one, see how it's going away from you, where the blue one is coming out towards the camera. The page should be sitting between the two of them like this. So what I've just done with these two pens is exactly what this right here is meant to show. The dashed one is supposed to be the red one going behind the page. The wedged one is coming like the blue pen straight out at you. And the page will be sitting right here in the middle. Okay? You can convince yourself of this using pens or anything you want. You can use toothpicks with little candies on the end of them. So that's what that means. So we could put, you know, one of the orbitals would follow them like that, the other one like that. You get your hydrogen overlap just like that. This one will be the same thing. So you're going to have like that, the orbitals, hydrogen, the orbital, hydrogen, right? So now, if we had, let me get my pens again here. So now what I'm going to draw is one of those hydrogens of a carbon where my hands are is coming out, the other one's going behind. So now you're actually going to have a p orbital. The p orbital will sit in the plane of the page like that. So I can draw it in the plane of the page, 90 degrees to both the red and the blue pen. So when we draw the p orbital, because we know this is a py, it's literally in, x and y is the page. This one will have the same thing. So you can see how these drawings, you really have to practice and have some pens or toothpicks or something, or an actual chemistry set that lets you put the pieces together to see it. So that is what it looks like. And I guess the other thing is, if I was to redraw it just like this, some people will say, okay, let's take a closer look at this. And specifically, if I want to look at the pi bond, look at it from the side. So if I'm looking at it from the side, I would see the two carbons, one on top of the other, right? Above, you would see some electron density like this, and below. So when you're looking at it from the side, you see this electron density on top and below, just like this. And then between these two carbons, you might see a little extra fuzziness like this, because what you're looking at is this overlap right here, straight on, the cylindrical kind of symmetry that obscures your two carbons topped up on each other. And then what you're going to see, 90 degrees to this, is you're going to see sort of, you know, like this, out the back. You'll see the two hydrogens in that. So that's the idea of what you can do and look at. Okay, so that's how you would draw that. What we could do now is carefully look at the triple bond, acetylene. The best way to start these out is to use a little bit of factual memory and practice that one of these will be a sigma, and what that means is you're going to have to use some kind of SP with certain thing. Do I have two of these? Do I have one of them? We'll get to them. But you know it's a hybrid orbital. It's going to look like this to make the sigma. The next two multi-bonds are going to be pi type. And what that means is you'll need p orbitals to do the overlap. Standard sigma single sticks in organic vil, standalone single sticks, you know they're hybrid orbitals overlapping. Unless you're hydrogen, then we just say, look, let's just say it's s orbital does the overlap. But hydrogen's special and easy in that sense. But we already knew that from our previous single stick model. Okay, so I need two p orbitals left. So if I was to draw, and I'll make this carbon 1, carbon 2. So I'm carbon 1 by itself. If carbon 1's by itself, we know it looks like this. Well, how are we supposed to make 1, 2, 3, 4 sticks? And we all know that the number of electrons, each of them has 4, right? This carbon I've used circles, 4 unpaired electrons to make the 1, 2, 3, 4 sticks. This one needs 1, 2, 3, 4 of its own electrons unpaired to make 4 sticks. So carbon 1 doesn't have enough, so we know it's going to hybridize. Now it turns out we already knew from up here to make 2 pi bonds, 2 sticks that are pi bonds, each one is going to have two p orbitals, so that's why we're going to leave two of them alone to make this one. So what we're circling to do the hybridization is these two are sp orbitals. They're shaped like that, right? And these are the remaining two that did not hybridize. It's a model, so we got to get used to it, and we have to apply it this way in Organicville. 1, 2, 3, 4. So you're going to break the off-Bauer filling rules, and you'll fill them in like that. Why? Because we know we need it to make this model work. Okay, well, this carbon 1, which is down here, and obviously we know that this one is, now we know, sp. This one will also be sp. They essentially have to have the same hybridization to make the bonds work. So carbon 2, we'll draw it up here. It has its two sp2s. It has its two remaining p's. And this was carbon 2. Hybridized. Okay. Well, carbon 1. We need to make sure that it's going to hook up with, call this hydrogen A, we'll call this one B. So hydrogen A, it needs to use up one of its hybrid orbital electrons to bond with hydrogen A. Done. It needs to use up another one of its hybrid orbital electrons to make a sigma bond. So this with carbon 2. Carbon 2 will use up one of its hybrid orbital sp electrons to overlap with the hydrogen B. So carbon 2, we'll say it has a hydrogen B. We know it's going to do that. And then they will simply hook up and make the first pi bond, the second. So you could call this pi 1, and you could call this pi 2. Now, remember how we said in hybrid world, in Organicville, we're going to ignore these pi bonds and p orbitals for last. Pretend they're not even there. This is where you play the little game as a procedure where you say, okay, what's in this rectangular box is any type of the carbon, let's start it with carbon 1, two regions of electron density. Therefore, two regions as far apart as possible. The geometry will be linear, right? Two ends. Ignore the p orbitals for now. Carbon 2 has one going one way, one the other way. We know that the hybrid orbitals look like this, right? They overlap. The other one points this way for a hydrogen overlap there. These each use one in the middle. That's the sigma bond between carbon-carbon. And then you have the other hydrogen make an overlap like that. So I think we've just drawn the pictures for that. So now what I'm going to do is, because this is perfectly linear, I've already handled all of this is in the plane of the page. So what we're going to do is we're going to need this Y, and this one's supposed to come out of the page. Well, we know that the remaining two p orbitals we're going to use, one of them is the py orbital, which is in the page up and down. The z-axis is going to have to go this way. It's supposed to come out and behind the page. Hard to draw that on two-dimensional things, but the way they do it is we can even kind of install an axis on each of them. We know that this Z1 is supposed to be coming straight out at you and behind the page. The Y1 is, if the Y orbital was my red pen, it would be in the page just like that. The other carbon could use its py, and they would overlap top and bottom. For the Z1s, it'd be like each one is coming out like this, and they overlap this way. Okay? So now you have to draw it in, and the Z-axis goes behind, the page like that. So you almost have to draw on the back lobe of the p orbital. I'm exaggerating the Z1 because so it overlaps here, and it overlaps behind. So this was the PZs overlapping to make what I could call, I'll just call it pi 2 bond. The second p orbitals are the y direction. So it's going to go, and I'll make it super high and super low. This is the py on carbon 1, and this is the py, exaggerated for drawing, py here. And we say they overlap like this. So this is called the second, or the first one, if you will, and then the other one will be the second. Doesn't matter what number you give them. As complicated and weird a looking as drawing as you see, this is exactly what organic textbooks and all that are going to use. This is what you have to do for carbon bonding, Bill. So that looks okay. So we have that. We could move on now to someone saying, well, let's do what we talked about. The analysis for this. Okay? Well, right away, you're going to say the same thing. In organic moleculeville, one of these sticks of a double bond or a triple bond. The first one is always a sigma bond. And what that means is you have to... Now, in this case, we're already quickly realizing, because remember, that's going to be sp2 hybridized. This will also be sp2 hybridized. So therefore, this sigma stick will be used when they each use one of their sp2 hybrid orbitals to do the first overlap. In fact, this one we're going to ignore, in a way, drawing until the very end. That is a pi bond, and that comes from remaining p orbitals overlapping with each other. So when we do each one's hybridization, I mean, if I was going to draw the full thing, I could say, let's use oxygen up here. And that's 2s, and that's 2p. You don't, this up front, you don't have to draw this. You could just right away draw the hybrid orbitals and draw the picture. But if you want to sort of walk ourselves through it, this is carbon here. So this would be oxygen by itself, and this would be carbon by itself as an atom. And we know it would be configured like that. Each one is by itself. Let's pretend there's like a magical barrier. They don't feel each other yet. This is what it is. But when they go to bond to make a double bond between each other, we know that each one is going to have to be sp2 hybridized. sp2, Mike. That's the remaining one. So this one is going to go 1, 2, 3 in a remaining p orbital. These will be your sp2s, the three of them. Right, and this is oxygen hybridized. Down here you get 1, 2, 3, and 1 up. 2p carbon hybridized. 1, 2, 3, 4. We purposely put an electron in each. We ignore the original off-bow filling rule for this type of modeling. So now we go back up here and say, what do we got? The oxygen has, in a Lewis diagram, 2 lone pairs. Well, guess what? They're right here, right? Each in this model, each sitting in an sp2 hybridized orbital, so to speak, on the oxygen. The hydrogen has 2. We know that this carbon, I'll use triangles for it, has 4 electrons it comes to the party with. And then we could say each hydrogen brings its own electron. So you'd have 1 hydrogen doing this, 1 doing that. Then the sigma bond is when the oxygen and the carbon use their electron, that's in an sp2 orbital, to overlap. The remaining, now we'll go to the remaining p electrons orbitals, pi bond gets made. Sigma, carbon-oxygen bond, this is pi carbon-oxygen. And we all know, again, if I look at the carbon, 1, 2, 3 regions of electron density, which dictates the carbon has no choice but to do that. I'm going to draw it this way for the geometry. We know it's trigonal planar, but I've tilted it like you remember, right? I've tilted it to look like this, right? And there's a hydrogen, This carbon will do the same thing. Oxygen. And yes, you don't panic. You're going to draw this. You draw that. And at the end of it, you say, these will get the lone pairs for oxygen. Still in trigonal planar geometry for the hybrid orbitals. It's going to have 1 more facing in like that. This one's going to use one of its to overlap, make the sigma. This one throws 1 out this way and this way. This hydrogen has its s orbitals, overlap. And then the remaining thing is the p orbital, which we would say is like a py in the plane of the page. That is a diagram for that one, right? Now what's interesting is notice how you're just going to automatically know from practice that a Lewis acceptable structure for formaldehyde will be that, right? So easy to draw. Notice how I put these on an angle already. Why? Because I already know and can't help myself that this is going to be 120 degrees. Because the hybrid orbitals, 1, 2, 3, are trigonal planar. The p orbitals don't get drawn here. This extra pi bond, we don't draw it in automatically in a Lewis notation structure, right? For organic, right? So that's okay. Now we could look at nitrogen. You know, how do I know it's already this way? Well, one of the things that we're going to learn, and I think if we haven't noticed already, this is us thinking carbon, nitrogen, and oxygen. How many sticks include lone pairs can they make? And the answer is 4. Now, isn't it interesting that you may use up one of these so-called sticks to put a lone pair dot on it? So look at nitrogen. How many bonds can it make? The lone pair almost counts like as if it was a stick or a region of electron density, right? 1, 2, 3, 4. What about this one? 1, 2, 3, 4. Okay, what if I'm carbon? How many sticks can carbon make? When you know when you take into account even the double triple bonds, this carbon can make 1, 2, 3, 4. How many sticks or regions of electron density can oxygen make? Somebody would say, well, it only makes 2 bonds. Okay, but notice how I'm saying sticks when you're carefully drawing a bond, but you're also carefully drawing in a lone pair as well. The lone pair almost counts as a stick in quotation marks, if you get what I'm saying. Regions of electron density. You know damn well there's going to be 2 other sticks, but they're just occupied by lone pairs. And I think we already seen that for the sake of drawing geometry, we put the sticks in to emphasize the shape. At the end of these sticks, when required, we put dots for the lone pair, then draw it. But the concept of a stick for stereochemistry purposes is good to draw it in. So all of them, you're essentially going to be putting in 4 sticks. Carbon does not have any of its 4 sticks used with a lone pair. Normally, unless you have a special charge, in normal neutral bonding, it'll always look like that. So this is how you automatically know if I'm making, what if I'm going to make O2? So what you're going to say is, I know it's going to make 4 sticks, but you also know that oxygen has those lone pairs. So right away, you're going to quickly learn oxygen makes 2 sticks for bonding purposes normally, and then the remaining 2 sticks will have lone pairs at the end of it, right? So even though people will draw it this way, say, oh, it only made 2 bonds. Well, yes, but it also has 2 other positions of lone pairs. So the more you practice this, the more you get used to saying things this way and thinking of it this way. And that's why it's so much easier to draw it quickly. So going back to N2, a little bit of it is memory, and a little bit of it is knowing this fact of 4 regions of electron density for these ones. So doing the analysis, you're going to have each nitrogen that's going to be, in this case, we already know one of these is a sigma, the other 2 are pi's, right? So these are each going to have to be sp hybridized. So each nitrogen is going to look like this. So you could call this nitrogen 1, nitrogen 2, nitrogen 1, nitrogen 2. These are when they're by themselves. They're going to go sp hybridized, 2 p's remaining, right? And they each have 5 Looks like that. So they are going to have a lone pair. They're each going to make the sigma bond. They're going to overlap this. The stereochemistry is governed by the hybrid orbitals. These are the S, and there's 2 SPs on each of these nitrogens, hybridized. Okay? So each nitrogen is going to be linear with a hybrid orbital pointing one that way, and this one's going to get a lone pair. This one's going to get a lone pair. And we kind of know that just from getting used to knowing how this is going to play. Plus, each has a lone pair. So we put it at the ends, and then it uses another one of its sp orbitals to overlap like that. That makes the sigma bond. And then you're going to have to put in the z-axis, the y, just to get your bearings. So the z-axis, we're going to do this. They overlap. Then the y-axis, I'll exaggerate this just so it's easier to pick it out which one we're talking about, right? The 2 pi orbitals, there's one and there's the second one. This is what it's going to look like. So I think we're okay with that. Other comments to make in this. I think we're pretty good in that department. A couple other fine points. I really don't know if you'll see this too much, but what if somebody said, well, this might be a little early for first year. I can't think of the textbook if it had questions like this, but why not? What if you had CH3 plus versus CH3 negative? So right away what I'm thinking is this. I'm looking at this and I'm thinking methane is neutral, and we know that methane, you're going to quickly learn this in Organicville. If it was CH4, this would be sp3 hybridized. It'd be tetrahedral and will look like that. Now, in effect, it looks to me like what you've done. And the other analysis you're going to have to quickly think of is you say to yourself, okay, this carbon came to this bonding party with, if it was CH4, that's what we're thinking of first, because it's easier. And each hydrogen brings its own electron to make those sticks. So first of all, what did we do from methane going to here? Well, we lost a hydrogen literally itself because there's only 3. And there's a positive charge. Now normally you're going to say the positive charge has to sit on the carbon itself, but the only way that you can get a positive charge on carbon is it has to actually lose one of its electrons that it owned. So to make this happen, you would essentially have to take, it doesn't matter which one, you'd essentially have to take this away. So you're getting rid of hydrogen, but in order for the carbon to be sitting with a positive charge, it has to lose one of its original electrons it came to the party with. So this has to be taken out. So you would have to draw the rest of this. And here is something you basically just have to pretty much memorize. You're going to have to realize that a carbon with either a positive or even a negative is going to be sp2 hybridized. Right? To fully appreciate exactly why that's the case, we almost have to trust the fact that it simply must be so. And it's not like you're going to have to memorize millions of different situations. There's only 2. A carbon with a positive charge literally on it in Organicville is going to be, in this case, sp2. And if it has a negative directly on it, it's more than likely going to be sp2 as well. So what does that mean? If the carbon is sp2, it has 3 sp2 orbitals with a 2p. And so this is carbon that's been hybridized. 3 sp2s. 1, 2, 3. Now notice how we said this carbon is going to have lost one of its electrons. So it's only going to have 1, 2, 3. So what they're going to tell you is, let's pretend that in this case you have, so this is carbon with a +1 charge. It's going to be sp2. 3 electrons will remain here, but this will be vacant p orbital. So we ignore that and we say, how's this going to be? Well, the carbon is going to go 1, 1, 2, 3. You're going to have 3 of these hybrid orbitals. It's going to have 3 hydrogens like this. And then you're going to have a vacant p orbital. This is a model. This is the convention. Well, we said this before in pure quantum mechanics. No orbital such as this one exists unless you have electron density in it. But for the sake of the geometry of how this likes to stay bonded, it's going to look just like that, right? And if we go towards this one, you could say, let's redo methane. Let's redo methane. And let's look at carbon's electrons. All right, so if we do finish this, I got sidetracked here. So we knew, same diagram as over here. If we were talking about neutral methane, and we're supposed to look at how we might recreate CH3 with a negative, well, first of all, we're missing a hydrogen. So yet again, I mean, I'll pick on this one because it doesn't matter which of the 4 that I choose. And to get the negative, well, we need carbon to acquire ownership of an extra electron. Every time you have a stick and 2 atoms are sharing an electron, as far as the official charge on an atom, we would say that officially this carbon at the moment has its 4. And each hydrogen has its own. But what if somebody was to give this hydrogen nucleus, the proton, the boot, leaving its electron behind? So you would be left with, something that looks like this, right? And technically, you would have a negative charge because this carbon owns its 4 plus this one with no other atom to share it with. Therefore, it has a negative charge. And off to the side of VH plus. And we already said this is sp2 hybridized. So what you would have is 1, 2, 3. And you would have the 3 sp2s orbitals on the carbon. And this would be the remaining 2p. And then you would have 3 hydrogens. And this is the extra. So this would be carbon with a negative charge on it. And the negative charge is almost like the extra electron that we said was a triangle is sitting right there. And then the way to envision this is, again, the geometry would be the carbon is trigonal, planar, and the sp2 orbitals, and you'd have the remaining p orbital with the extra electron and the negative charge in a p orbital. So it's sp2 hybridized, right? So that's another way of looking at this. So folks, I think as far as the organic, maybe I could do one more thing just to give you an idea. So what if somebody had, methanol looks like this. So basically put, you have a carbon that's tetrahedral, and let's say we use this one for the oxygen. The oxygen is also going to be tetrahedral, like this, and you're going to get lone pairs, like that. Now, what would happen, and each is sp3, okay, because in the world of organic, each of these, I mean, you could draw it out this way. They can, without showing stereochemistry, a lot of them will simply do this. They'll show you all the sticks. And anytime you see single sticks in organic chemistry, right away you know that the carbons, the oxygens, and the nitrogens are sp3 hybridized, which means they're tetrahedral. They make 4 sticks, just like this. And you can put your lone pairs in if you're nitrogen or oxygen, like this. What I wanted to cover was the very idea of what if some acid, an H plus proton. Well, what's interesting is this lone pair can actually pick it up. So let's draw what we'd get. You'd have your carbon. You'd have, now you've essentially made a new stick with the 2 electrons that used to belong in a lone pair to oxygen. So now this neutral entity picked up a positive quantity. So now they're going to put the positive directly on oxygen. So the answer, one of the regions is Y. So let's blow this up for a minute. You've got a lone pair. You've got this. So going back here, let's draw it this way. And we'll use a square for this one. So when we started off, oxygen had 1, 2, 3, 4, 5, 6 of its own electrons. The lone pair was its own. It had covalent bonds with the 2 side things, but it had ownership of 6. The same number that it came to the party with, therefore it was neutral officially here. Picks up an H+, it turns into something like this. Well, look at what's happening. You made a stick, but do you see how you have a new covalent bond stick, if you will? So this hydrogen has essentially, officially, to complete the rule, each has its own unpaired electron. It's taken one of these 6 electrons. So now this oxygen only has 5, leaving it with officially a +1 charge. And this is another reason why in organic, anytime you see an oxygen with 3 sticks, it automatically has a positive charge on it. This is a common idea of what takes place, and this is called, housekeeping or accounting for the electrons that maybe you started with ownership with, and whether you pick up an acidic hydrogen, such as a proton, why do you get to put a positive on oxygen, for instance? This type of bonding, and even this type right here, where we talked about a positive or a negative carbon, even though it looks like a simple molecule, you might see some of the harder questions in bonding in our first year book where they might write something like this and say, suggest what the bonding is like. But that's about as far as it goes for first year. So I think we're good for the organic. So signing off on this section, we were talking about first year organic molecules where we changed the rules of the single bond molecule which we opened up with. We changed a few rules a little bit specifically for carbon, nitrogen, and oxygen for the most part. Okay.